that whatever confusion you were having is really clarified today. Okay, so we're going to really keep going on what we've already been doing and not jump into a lot of new stuff, and this should really help. Okay, so all this stuff, the first derivative, the second derivative, concavity, increasing, negative, positive, it's like it starts. I know that when you're first getting into that, it's like this jumbled mess, and it's like it's so hard to you come to a new problem, and it's like you didn't learn anything in the previous problem. Okay, so here's the main idea. This is like 80% of it right here. 80% of all this stuff is getting this main idea now. So I want you to fill in the blanks. We're not to the sheet yet. Okay, we're not to the sheet yet. Just keep the sheet on the side. That's the next screen. Okay, so here's the main idea. Can you fill in the blanks somehow that makes sense? So the rate of change is blank when the function's output y is blank. Can you fill in the blanks so that we have an equivalence here? We have two equivalent statements. All right, see if you can do that. Talk to the person next to you. So can you fill in the blanks here so that you have equivalent statements? There's two ways to do it, okay? There's two ways to do this. Can you come up with a way that makes a true statement? Okay, so I'll give you a hint. I'm going to tell you that so this is our left and right graphs, right? This is our rate of change graph on the left, and our accumulation graph on the right, right? So this is, relating this back to what we did all semester long. Rate of change on the left, accumulation on the right. So I'm going to tell you that the accumulation is increasing. The accumulation is increasing. Now fill in the blank for the other one. Accumulation is increasing. Okay, what does the rate of change have to be? The accumulation is increasing, the rate of change is positive. Okay. So this is a fact that we want to memorize. It's going to empower us to do lots of problems and all kinds of things, like all those problems that you did yesterday for web work, all the optimization stuff that's coming up. This is a fact we want to memorize, but we want to also understand why it's true. So using the fact that k equals delta y over delta x, can you justify this? Can you prove that this is true? That if the output y is increasing, so we're going to say if the accumulation is increasing, then the rate of change is positive. Can you prove it given the fact that k equals delta y over delta x? Talk, see if you can do it. Can you prove that the rate of change is positive if the accumulation is increasing? Go. Okay, so we've got an increasing accumulation. We want to prove that the rate of change is positive. So here's what a good proof would look like for that. See how it compares to what you said. If y is increasing, then the final y, or y2, is greater than y1, right? Which means that the change in y is positive, because y2 minus y1 would be positive. And so then, for a positive change in x, you got a positive change in y, therefore the rate of change is positive. There's a good proof of this fact that we want to know. Does it make sense? Okay. Do it again. If the function's output y is decreasing, the rate of change is negative. Prove it. Go, prove it.
If any one of them is negative, it's still negative.
But we always take a...
Isn't this the question of the day?
Okay, prove that if the accumulation is decreasing, the rate of change is negative. Prove it.
Even though x is a positive values, it's basically what it is as well.
So it starts with comparing y2 and y1. If it's decreasing, if the accumulation is decreasing, then how does y2 compare to y1? How does y2 compare to y1? Less, right? The final y is less than the initial y. So what about delta y? Negative. Delta y, the change in y, is negative. Therefore, you've got a negative change in y divided by a positive change in x, which gives a negative rate of change. Okay. So yes, we're memorizing this fact and we're using it all the time, but you should know why it's true. It's an easy little proof, right? Using the change in y. A final y and an initial y. Okay, so that's it. If the values of the derivative are positive, values of the function are increasing. If values of the derivative are negative, values of the function are decreasing. This is 80% of the whole thing, because watch. This is true for any function and its derivative. It's true for an accumulation function f and the derivative. All those facts are true. But then it's true for the first derivative and the second derivative. Why? Because the second derivative is the derivative of the first derivative. So all these facts apply. The same framework applies when you're comparing the first derivative and the second derivative. If the first derivative is increasing, the second derivative is positive. If the first derivative is decreasing, the second derivative is negative. So this is it. Okay? This is really, like I said, 80% of it. There's just one more idea that we add to it, and we've got the whole picture. So one more additional idea completes the picture. That is, in this first case, where the second derivative is positive and f prime increases, then what about f? So if f prime is always increasing, then our function turns counterclockwise. Our function turns counterclockwise. So we have concave up. Okay, and then in the second case, where the values of the derivative, so if the second derivative is negative and the first derivative decreases, then f turns clockwise. The rate's getting less positive and more negative, so we get concave down. And that's now we're at like 95%, 99% of what you need to know to kind of make your way through any kind of problem where you're relating derivatives and drawing graphs and things like that. Okay, any questions? So again, it's about this right here. It really comes down to this. If a function is increasing, its derivative is positive. If a function is decreasing, its derivative is negative.
So it was counterclockwise, it's increasing.
What's it?
I'm sorry, I apologize. one line where it says f double f prime of x is less than 0, and that's the other way around, it would be counterclockwise, right?
Yeah. Okay, so we're going to start talking about optimization. So optimization is about a best value of accumulation. So best. What do we mean by best value of accumulation? The greatest? Greatest value of accumulation?
Best.
No, it could be the greatest. So we're talking about the greatest value. Like if we're talking about a quantity of profit or runs scored in a baseball game, we want the most, right? We want the most. But that's not all cases. Sometimes the best value of accumulation is also what? The least. Okay, so when we talk about optimization, it's like we're looking at the output of the accumulation function, and we want that to be either the highest or the lowest, depending on what our quantity is. Okay? What do we want? We want cost to our company to be the lowest, right? Etc. So critical values is what helps us optimize a function. So critical values of a function is any value of x where the function exists and either the first derivative is 0 or the first derivative does not exist. So we have to have a valid output of the accumulation. And then we have a critical value if the derivative, the first derivative equals 0 or the first derivative does not exist. We're going to spend most of the time focusing on when the first derivative is 0. Okay? So, if the first derivative is 0, then what are we saying? We're saying the rate of change is 0, or the accumulation is not changing. Right? If how fast it's changing is 0, then it's not changing. It's constant. So, in terms of changing functions, we're talking about that the accumulation stops or pauses momentarily, increasing or decreasing at the value c. So for a moment, the accumulation is constant. We call that a pause. Okay, we're going to call that a pause. Accumulation pauses for a moment. Okay? And that makes sense because 0 means the rate of change is 0. It's not changing. Okay, so what different situations can we have for a pause, for the first derivative equal to 0? Okay, what different situations can we have? So that's what we want to look at. Okay, the first one is, just a minute at the end, not since we're there yet. Okay, the first one is a local max. Okay, you can get your sheet out now. Don't write on it yet. Listen, pay attention. So a local max is like this, an accumulation. In some area around C, we have this situation. So I want you just to watch. First, okay, so first one I want you to watch the value of the x, or the input coordinate, okay? Watch the value of the input coordinate, so the black arrow. That's what we're going to watch first. Watch the black arrow. Okay, what's it doing? Okay, so it's really boring, right? It's just increasing. So our focus is on what? The input or the output of the accumulation? The output. Okay, so we're interested in what the output of the accumulation is doing. So we're going to force that input just to make a steady increase so we can get a good picture of what the output's doing. Now I want you to watch this arrow. This is representing the current value of the accumulation, okay, for whatever the input is. And this is embodying what a local max is. There's 3 parts to it. There's 3 parts to a local max. When you watch that output quantity, and you watch the value of that output quantity represented by that arrow, what's the first part of understanding of a local max? What happens to the output of the accumulation at a local? Increasing, right? So increasing to the left of C. And then what's the second part? What happens at C? Do you see that it pauses? Watch, pause. See it? Watch it again. Ready? Increasing, pause, decreasing. You get a pause at C. And then what's the last part? This is what characterizes a local max. Increasing output, a pause of the output, decreasing output. So now what you're going to do is, have you learned something? What does this mean for the rate of change? So break it up into 3 parts. You got 3 parts. The function increases, the function pauses, the function decreases. What does it mean, each part, for the rate of change? And then can you make a rough sketch of what the rate of change will be like for this local max situation? Give it a shot. Go. All right, let's see what you have. So this is the this is what the sheet is for. So this is the first row on your sheet. Okay. Okay. Okay, last people got it. Remember what we said. If the function is increasing, then the rate of change or the derivative is positive, right? I said it's 80% of it, and here it is. If the function's increasing, the rate of change is positive. What does that mean for a graph whose y-axis is rate of change then? We want the rate of change to be positive. What does that mean? Yeah, say it. Above the x-axis. So over here, where the function is increasing, the rate of change is positive. We're up here. And then the accumulation pauses. What about the rate of change? 0, right? So if accumulation isn't changing, how fast it's changing is 0. So we know we got that point. At C, we got the point 0. And then, if a function is decreasing, what about its derivative? What about its rate of change? Negative, so down here, right? Down here. So when the accumulation is increasing, the rate of change is positive, up here above the x-axis. Okay, so yeah, if you have a straight line, that's perfectly fine. So this is what the rate graph looks like for a local max. A positive rate of change, increasing accumulation. A 0 rate of change, the pause. And then a negative rate of change, decreasing. So we're breaking this down because we're going to get into these optimization, these real-world problems, and we're going to be like on the hunt for local maxes and local mins because that's the best. The highest value of accumulation or the lowest value is the best. So we want to know really well, what situation are we looking for? So if we're looking for a local max, when it comes to accumulation, we're looking for this. Increasing, pause, decreasing. And when it comes to the rate, we're looking for this. Positive rate, 0 rate, negative rate. Okay, and then one more thing. What about the second derivative? So now that we have our first derivative graph, what is the first derivative graph doing? What is it doing? What's that rate graph doing? Decreasing. If a function is decreasing, what about its derivative?
It's negative.
Negative. So how does the graph of, what will the graph of f2, second derivative be? Down here. If a function is decreasing, its rate of change is negative. And if the second derivative is negative, what did we say? The original function is? Concave down. There it is. Look, so at the local max, it's concave down because the second derivative is negative. Concave down at a local max because the second derivative is negative. If you want to sketch in that second derivative graph, you can. Any questions? Does it make sense?
So far.
This is so. Here's the thing. These optimization problems are very, very difficult because they're from all contexts of science and geometry and business and math and economics and everything. But these are the things that are common to all those problems that you're looking. So if we're on the hunt for a local max, these are the things we have to know that we're on the lookout for. Okay, so you try local min. Go. So local min. First, the accumulation. What are the three parts of the accumulation function for local min? Then what will the rate of change be like, the derivative, based on that? And then what will the second derivative be like? Okay, first part to a local min. The accumulation first does what? What's first for the local min? Decrease. To the left is coming down. It's decreasing. Then?
Increases.
Pause at the bottom. Accumulation pauses at the bottom, and then?
Increases after the pause.
Then it increases. So if a function is decreasing, its derivative is?
Positive.
Listen, Eric. If a function decreases,
It's negative.
the rate of change is negative. We're going to be down here. At the pause, rate of change is?
0.
0. Right? Flat line. Right? For a moment, constant rate of change. And then? Increases. Rate of change is?
Positive.
Positive. Something like this. Okay? And so then what? Our resulting rate graph is what? Everywhere. It's what? How can you characterize that rate graph now?
Positive.
Nope. It's negative here and 0. But everywhere that rate graph is increasing. If a function is increasing, its derivative is
Positive.
positive.
I was thinking of the derivative.
If the second derivative is positive, the original function is
Concave up.
concave up. Why? Because the rate of change is increasing, meaning the rate is getting less negative or more positive, turning counterclockwise. So these are the situations we're on the lookout when we're in these optimization problems. All of them are like this. We're looking for a local, some kind of maximum of accumulation or some kind of minimum of accumulation. And so we have to know what the derivative is like, right? We have to know what the first derivative is like and the second derivative is like to really pinpoint where we're going to have either a local max or a local min. So when the first derivative is 0, is a max or min guaranteed? So we find that the first derivative is 0 at some x value. Do we know that we have a max or a min? What else is there? There's other stuff that could happen. We'll call them rest stops. You're driving down the highway. You gotta go. You gotta get a Snickers. You gotta do something. You pull over at a rest stop. And then what happens when you're done with the rest stop? Do you turn around and go back? No. What do? You keep going the same way you were going. So we could be increasing and then pausing for a moment and then increasing again. Is it a local max or min? No, it's like increasing the whole way except for that one moment, right? There's a pause. So a rest stop, okay? You do the rate of change graph. Can you come up with the rate of change graph that corresponds to what we call a rest stop, type 1? Let's see if you can do it. Can you get the rate of change curve for this?
It's increasing. So yeah, rate of decrease. Yeah, so that's why it's not negative. It's increasing. It's always increasing. Slope graph right there. We think about it as the slope lines. Always positive, right? That's why it's always going to be above. So this is
Draw. So and then sketch the second derivative. If you want to try sketching the second derivative, what would that be like?
yeah, you're still accumulating. You're slowing down, stopping, stopping. So like this line here is so fast, this line's slower, this line's slower. It's like zero. And it's like all different levels. Never the tangent lines are never slow. Lines, the tangent lines are never slow. So it's like slower. So this means that
Okay. If a function is increasing, the derivative is? And they all said in chorus? If a function is increasing, its derivative is? Positive. Up here. When a function pauses, its output pauses, derivative is? 0. When a function is increasing, positive. So we're going to be up here, then 0, then up here. Okay, some of you had you made like lines with a point. So it's really, to be accurate, it's going to come down. It's going to be more curved like that. It's not just going to make a V, okay? It's going to come down and kiss the x-axis and then turn and go back. All right, so if we were sketching the second derivative, now we're looking, so to graph that, we talked about positive, 0, and positive. But now to sketch the second derivative, we need to talk about increasing and decreasing. So less than c, what are we doing? Decreasing. So the derivative of that would be negative. So this function's decreasing, so its derivative would be negative down here. Over here, increasing. So its derivative would be positive. Did you get it?
Got it.
So that's what the second derivative will look like for a rest stop. And it makes sense. Look, negative second derivative means the original function is concave down. Positive second derivative function is concave up. Okay, so can you draw rest stop type 2? Can you draw it yourself? So what would the last case be for a pause of the accumulation? It'd be a rest stop type 2. How'd you do? So what's this about? We're heading home from vacation, right? So, decreasing, then pause, then you keep decreasing. You keep heading home. You're heading home, stop for snack, and you keep heading home, decreasing.
Time for Snickers bar.
Okay, decreasing function, negative rate of change. Pause of the accumulation, 0 rate of change. Decreasing function, negative rate of change. Second derivative. Increasing.
Positive first.
So this is increasing and then decreasing. Positive, then negative. So here's the deal. So you're going to come to these optimization problems and you're going to have this accumulation function, and we're on the lookout, we're on the hunt for local max and local min. Just because we've got x values where the first derivative is 0, it means it could be any of these 4 cases that you just did on your sheet, that we just did. So we have to know more than just the first derivative is equal to 0, because there's these 4 different cases. So we have to look at other things. We have to look at the first derivative. We have to look at the second derivative. And those first 2 on your sheet are what we're looking for local max and local min. And we want to be aware of these, but in terms of optimization, these rest stops aren't going to be what we want. Okay? They're not going to be an optimal value of accumulation. But we need to be aware of them and know how to dissect them as well. Okay, so then I also said that critical values are where the first derivative does not exist. So there's 2 cases for that. One case is if you have a corner point. So we'll just do this real fast. We're not going to spend a lot of time, but all right, so right there is also a critical point, but the first derivative does not exist because coming from the left, it looks like it's this positive value, but then suddenly, it's like on that point, it just suddenly changes to a negative rate of change. So the rate of change does not exist at that corner point, but it's a critical value because look, it's a local max. It's a local max. So that's the idea of a corner point. First derivative doesn't exist, but it's critical. All right. The other one is if your graph is momentarily vertical. So just for a moment, it heads north, right? So you have what? It's like the slope it's like a vertical slope, which we know that does not exist. Okay, it's like delta y over delta x, where delta x is 0. You're going to get a change in y for a 0 change in x, undefined. Okay, so that's also a critical point. So be on the aware of that too, that those give critical points as well. Okay, let's do an example. So here we go. We've got some situations. So imagine we have some situations, geometry, or it's distance, or trying to get across a pond, or running around a building, or something, or profits. And this is our accumulation function. J, the output of J is the accumulation of some quantity. What? That we want to optimize. Meaning, we want to find the value of x that gives us the best value of accumulation, which might be the highest value of this function j or the lowest. All right, so we're going to start by trying to find, this is local. I like local better. Meaning it hits a max in its local area, right? All right, so determine numerically if J has any local maxes or mins, okay, or inflection points. Okay, so that's where concavity changes, and inflection points where the concavity changes. So if we're after local maxes and mins, how do we start that? How are we going to pinpoint some possibilities for local maxes and mins? Using calculus. Using calculus. So where are candidates? Where are candidates? Where? Critical points. Critical points, which are? How can we get a list of possible x values that are critical points? Yes, sir.
You said the derivative equals 0.
Yeah, like just that sheet we just did. We said local max and local min are critical points where the first derivative equals 0. Or undefined, right? So we want to get that first derivative. And we want to look for 0 or does not exist. Those are critical points. Those are our candidates for local max or mins. So you're all masters of the derivative now, right? Piece of cake. So the reason we do the mastery test is so this is like we can do in our sleep, right? We should be able to. Okay, so all those graphs and that reasoning we were doing, we're bringing that mentality to the algebra. Right? So all those graphs and analysis and logic and reasoning, if this is true, then this is true. We're still holding on to all that stuff as we do a more kind of algebraic approach here without a graph. So we got the first derivative, and what do we want to say about that first derivative? If we want critical points, we want that to be equal to 0. We want pauses. We want the accumulation to pause, right? We want the accumulation to pause. That's where rate of change is 0. So we have this thing then equals 0. So I'm going to say rewrite it here. So negative 3x squared plus 18x minus 15 equals 0. Again, we're looking for x values that make the first derivative 0. So we're going to solve this quadratic equation. What can we do first before anything else? Get the 3, get a negative 3 out of there. So x squared minus 6x plus 5. And then we get to, how do we solve for x? Some of you have been waiting all semester for a problem like this. Right? What do we do? Factor. Does it factor evenly? If it doesn't factor evenly, then what do we do?
Then we use a
Quadratic formula. Quadratic formula. So this does factor. How's it factor? X
X minus 5
minus 5
times x minus 1.
minus 1. What are we doing? We're trying to find x values that make the first derivative 0 because that will give us our candidates for local maxes and mins. Like that whole sheet that you just did. X equals
5.
1 and 5. So we got it. 1 is the local max and 5 is the location of the local min, right? All right, no, we don't know. These could be rest stops, type 1, type 2, local max, local min. So, what now? We need something else. Remember, local, so let's... Local max. Rate of change of J. So if this is the rate graph, right? If this is the rate graph, and we have some critical value, if it's a local max, what will the rate be like? 3 things. The rate will be like what, and what? Local max, right? Increasing, pause, decreasing. Therefore, rate is positive, 0, negative, remember? So one way we can check to see what we have is look at what the rate is a little bit. So we'll start with 1. Start with x equals 1. What is the rate a little bit to the left of 1? What is the rate a little bit to the right of 1? So put in 0. What do you get for the, so this is our rate function. If you put in 0, what do you get? Negative 15. So I'm looking at J prime here. J prime of x. To the left of 1, I plugged in 0. I got negative 15. And then at 1, we know it's 0. And then what about, say, at 2? Plug in 2. 36 minus 12 minus 15. 5? Is that right? 36. So what am I doing? I'm checking this scenario right here. I'm seeing what's the first derivative to the left and what's the first derivative to the right to see if they're positive or negative and see what situation we have. So when I plugged in a number to the left of 1, I got a negative first derivative. And then we know that at 1, the derivative is 0. And then when I plugged in a number greater than 1, I got a positive. Is it 5? Is that right? 9? Thank you. Okay? So what situation do we have? We have the rate of change. The rate of change of J, or J prime, is what? Negative, then 0, then positive. Meaning the accumulation is doing what? Decreasing, pausing, increasing, just like we drew. What do we have at x equals 1? Local min. Okay, x equals 5. You try. So you do the analysis for x equals 5. So you want to, for x equals 5, you're going to plug something a little bit less than 5 and find out if the derivative is positive or negative. Plug in something a little greater than 5 and see if it's positive or negative. Did anybody plug 4 in?
I got 9.
What do you get when you plug 4 in? 9? What do you get when you plug 5 in? 0. That's where 5 came from. 5 came from setting this equal to 0. All right? And then what happens when you plug in 6? 50? Therefore, that first derivative around 5, positive, 0, and negative. And that means for our accumulation is increasing, pausing, decreasing. At x equals 5, we have local max. So that's one way to figure out what your critical value is. You can look at just the first derivative. What's happening to the right and left of your critical value to determine what the situation is. What's another way we could do this? So here we are. We're just going to start again. I'll do this in red now. We've got our two critical values. We have another tool that can help us determine what kind of critical values they are. What's that? Second derivative. Find the second derivative. What is it? It's equal to? Back to the first derivative. 0, 18 minus 6x. Okay? At x equals 1, so j double prime of 1 equals what? 12. So look, we've got a critical value where the first derivative is 0 and the second derivative is 12. What does the second derivative of 12 mean for our accumulation function? Concave up. That the rate is increasing. The rate is increasing, getting less negative and more positive. So if it's concave up with a pause, local min. That's what we said. That's the same conclusion we made here using the first derivative. And then at 5, what will the value of the second derivative be at 5? 18 minus 30, negative 12. If the second derivative is negative and the first derivative is 0, we have a decreasing rate of change, becoming less negative and more positive. Concave down. Local max. So you can use, this is called the second derivative test. You can use the concavity by the second derivative to check if you have a local max or min also. Okay? So both are valid, right? Both are valid. You can analyze this using the first derivative, or you can analyze it using the second derivative. Okay, so then we have a 0 of the second derivative also. Okay, so what value makes the second derivative 0? 3. So let's see here. We have a local min at 1. So let's find those values here. Find j of 1. Now the actual accumulation at 1, the actual accumulation at 5, and the actual accumulation at 3, which is our, we just said, makes the second derivative equal to 0. Let's get those output values while I'm erasing here, okay? So get those three output values, j of 1, j of 5, j of 3. Anybody got j of 1? J of 5. 20? And J of 3? Cool. All right, so J of 1 is negative 5. J of 5 is 27. And J of 3 is 11. And so with that analysis, we saw that the rate of change was negative. And then we had a pause. And then the rate of change was positive. And at 1, second derivative was positive, concave up. At 3, we had that the second derivative was 0. That's going to be where the concavity changes. So from 1 to 3, it's concave up. And then starting at 3, because the rate of change, second derivative is 0, it's going to be concave down. And then this plays into what we got for what happened at 5. We said the rate of change was positive first, and then a pause at 5. And then the rate of change is negative. And we found the second derivative was negative, concave down. So there's a sketch of J using the derivatives.